Welcome back, class. I'm excited for today's lesson. Last time, we learned how to make a parabola flip upside down, get wider or narrower, or shift in any direction, just by making changes to its quadratic equation. Today, we're going to learn how to find the most important points on the graph of any parabola. Before we get started, does anybody have questions about the quiz I handed back last time?
I got 3 questions wrong, teacher, but I understand my errors. I am at peace with my grade.
How did you do on it, Codette?
Okay.
Bones, I think Codette doesn't want to brag, but she got a perfect score.
Wow, that's awesome.
See, Codette? Don't hide your light. Let it shine.
Thanks, Ruby.
If there are no questions, let's jump in. When we graph a quadratic equation, we know that the shape it makes is a parabola, this symmetrical two-armed curve. But to start today's lesson, I want to remind you what a parabola actually is. It sure looks like one smooth flowing curve, but actually it's made of millions and millions of individual points, like a huge game of connect the dots, where the dots are very, very close together. Every point on the parabola is one answer to the quadratic equation that made it. So in the equation y equals x squared, if I plug in the number 2 for x, then 2 squared is 4, so y equals 4. And on our graph, we have the point x equals 2, y equals 4 as one of the points on our parabola. A parabola is tons and tons of these single points lined up together, like a necklace made of billions of tiny beads strung together. Which means that when we need to graph a parabola, it's going to be impossible to graph every single point. Graphing an entire parabola, point by point, would take forever.
Like, literally forever.
Yes, as crazy as it sounds, there would be infinite points on a parabola, even just between x equals 1 and x equals 2. We could plug in x equals 1.1 and get an answer for that. Then we could plug in x equals 1.01 and get an answer for that. Then x equals 1.001. We could keep going forever without even getting to the number 2. I'm going to come back to this idea later in our lesson. This idea that there are endless, infinite points in a parabola, because we're going to see a different example of it, when the arms of a parabola keep extending outward forever. But for right now, here's the point I want to focus on. It's impossible to graph all of the points on any parabola. There are just way too many of them. So, if we need to graph a parabola, we're going to have to make choices. The only possible way to graph a parabola is to choose a few important points and draw the curve traveling from point to point between them, like a normal game of connect the dots, where there are only a few dots instead of billions of them. So, which points do we mark on the graph? Which ones are the quote-unquote important points? Let's look at an example of how this can go wrong, because that's going to help us understand how to do it right. Suppose that we have 2 points that we know are on our parabola. They're 2 random points that we've marked on our graph, and now we're ready to play connect the dots. We're going to try to draw the whole parabola using these 2 random points. Does anyone see the problem with this?
There are different parabolas you could draw through those 2 points. Only one of them would be the right parabola for our equation, but we wouldn't know which one was right.
Exactly, Codette. There are different ways to connect these dots. We could have a wide parabola like this, where both points are on the same arm. Or we could have a narrow parabola like this, where our 2 points are on different arms. In our last lesson, we saw that parabolas can be shifted up or down, left or right. We can make them thinner or wider, U-shaped or rainbow-shaped. So parabolas can come in all shapes and sizes, which means that 2 random points could have lots of different parabolas passing through them. Each one would have its own separate equation, so how would we know which parabola was the parabola for our equation? That's why we can't graph parabolas using random points. Yes, those 2 random points might belong on our parabola, but they would also belong on other parabolas. So we need to use the points that are helpful for graphing our specific parabola. Otherwise, we're just wasting time and confusing ourselves. So, what are those important points that help us graph our parabola? The first point that's going to help us a lot is the vertex, which is the turning point of any parabola. On a rainbow-shaped parabola, a frowny parabola, the vertex is at the very top, so we sometimes call it the maximum. On a U-shaped parabola, a smiley parabola, the vertex is at the very bottom, so we sometimes call it the minimum. Either way, the vertex is usually pretty easy to spot on a parabola as long as we have a graph to look at. So let's try it. Ruby, here's a parabola. What are the coordinates of its vertex? Where is its vertex located?
It's at the top of this parabola, the maximum, which is at the point 2, 3.
Good. Codette, how about this one? What's its vertex?
It's at the bottom of the parabola this time, the minimum, at 1, -1.
Right. Now let's move on to our second kind of important point. It's the x-intercept. The x-intercept is any place a parabola touches the x-axis. We're about to learn something tricky about the x-intercept. Instead of telling you what it is though, let's do some examples and see if we can figure it out. Tom, here's a question for you. This is the parabola of y equals x squared. We learned in an earlier lesson that we call this equation the parent function because it's the mother of all quadratic equations, the basic one that all other quadratic equations come from. So, what is the x-intercept of this parabola?
I have a good feeling about this one, Mr. Caldwell. This parabola sweeps down and touches the x-axis right at the point 0, 0. So that is the x-intercept, I think. 0, 0.
You're right. But what happens if I take the same parabola and just shift it down by 1 unit, using the technique we learned in our last lesson, subtracting 1 from the end of the equation? When our equation is y equals x squared minus 1, it makes a parabola that looks like this. So, V9, what is the x-intercept now?
Error. There is more than one x-intercept. There are two x-intercepts because the parabola touches the x-axis at 2 places, -1, 0 and +1, 0.
Excellent, V9. This actually happens a lot with parabolas. A parabola will cross the x-axis, then turn around and cross the x-axis again on its way back. So we end up with 2 x-intercepts. Which means that some parabolas have 1 x-intercept, like our first example with the parent function. But other parabolas have 2 x-intercepts, like this one. Now here's another question. What happens if I shift our parent function up this time, by 1 unit from where it started? This is the parabola of y equals x squared plus 1. Who can tell me what its x-intercept is now?
Teacher, this parabola no longer touches the x-axis at all. It turns around and heads backward before it ever reaches the x-axis. Therefore, it has no x-intercept, correct?
You got it, Wendigo. Some parabolas like this one have no x-intercepts at all. They never quite make it all the way to the x-axis. When we have a graph to look at, like we do right now, it's still usually easy to see how many x-intercepts there are. But in a later lesson, we're going to have to find these same points without a graph, just using the equation. And that makes finding the x-intercepts harder than finding the vertex, because while every parabola has a vertex, some parabolas have no x-intercept, some have 1 x-intercept, and some have 2 x-intercepts. That brings me to our third and final type of important point on a parabola, the y-intercept. You can probably guess what the y-intercept means. We just learned that x-intercepts are any point where a parabola touches the x-axis, so y-intercepts are any point where a parabola touches the y-axis. Let's go straight into an example. Bones, what's the y-intercept of this parabola?
Y-axis. Y-axis. That's the one that goes up and down, right? Like the vertical axis. This parabola crosses that axis at the point 0, 4.
Right. But what if I transform this parabola by shifting it to the right, away from the y-axis, like this?
This question is not logical. This parabola never intersects the y-axis.
Hold on, V9. I don't think you're right. Mr. C told us earlier that the arms of a parabola keep on going forever, so the left arm of this parabola must touch the y-axis somewhere. We just can't see where that happens.
Excellent, Ruby. That's exactly right.
So if we zoom out, will we be able to see where this parabola crosses the y-axis?
Good question, Codette. Yes, we can. This parabola touches the y-axis way up here, at 0, 36, which means we just learned something. Some parabolas don't seem to have a y-intercept, We look for their y-intercepts on the graph, and we don't see any. But don't be fooled. The arms of parabolas go on forever. They're still going strong even after our graph stops showing them. They're still going at x equals 1 million, and x equals 1 billion, and x equals -1 trillion. Even if we zoom out 100 times and still don't see a y-intercept, our parabola will have a y-intercept eventually. This teaches us something that's important to remember. It's impossible to draw an entire parabola, since it goes on forever. So any graph of a parabola is just showing us a part of that parabola, not the whole thing. To remind ourselves of that, sometimes we draw little arrows at the ends of the arms of our parabolas. It's a way of showing that the arms keep going far beyond the limits of any drawing. Does everyone understand?
I think we get it, Mr. C.
Good. Then let's review what we've learned today. When we graph a parabola, it's impossible to mark all of the points because a parabola is made of an infinite number of points, like a game of connect the dots that never ends. It would literally take forever. So we have to choose which points to graph. And we can't just choose any random points because many different parabolas can go through 2 random points. That's why we need to choose the most useful points. We want to pay special attention to the vertex, the x-intercepts, and the y-intercept. The vertex is the turning point of a parabola, and it can either be at the very top of a parabola, which we call a maximum, or it can be at the very bottom of a parabola, which we call a minimum. The x-intercepts of a parabola are any places where the parabola touches the x-axis. Remember that when we graphed our parent function, y equals x squared, it had exactly one x-intercept, because its vertex was sitting right on top of the x-axis. But when we shifted that parabola down, we saw that a parabola can have 2 x-intercepts if it crosses the x-axis, turns around, and then crosses the x-axis on its way back. And when we shifted our parabola up, we saw that a parabola can have no x-intercepts if it turns around before it ever touches the x-axis. Lastly, we learned that all parabolas have a y-intercept, which is any place where a parabola touches the y-axis. In fact, we learned that all parabolas have exactly one y-intercept, never 0 of them, and never 2 of them. Sometimes we can't see that y-intercept on a graph, but that's only because a graph, no matter how much we zoom out, is still just showing us part of a parabola. The arms of all parabolas go on forever, so every parabola has a y-intercept eventually. Good work today, class! In our next lesson, we're going to try something trickier. We're going to learn how to find the vertex and the intercepts without being able to look at a graph, using only the equation. But we've learned plenty for today. See you next time!